So hi everyone, as we have started our discussions on classical machine learning. So in that, so far we have covered k nearest neighbors, then we covered naive Bayes algorithm, and then logistic regression. Okay, still the probabilistic treatment is still pending for this logistic regression, and now from today's lecture we'll take linear regression. This will be the topic of discussion from for next 1 or 2 sessions. So now we'll see that here we have two terms. The first thing that you see is linear. Okay. The second thing that you see is regression. First we'll see what a regression is. Okay, what is a regression? I have defined it multiple times, but just for the sake of completion, I'll again define it. As you know that this comes again under this supervised learning. Supervised learning. So in that we have the class and data points, and we have class labels. So how do we represent our data set? So let's suppose we have the data set D. So mathematically we represent it like this. We have a pair xi comma yi. Xi, this is our data point. This has data, and this is data features, I'll call them. And this we call as label. And then we'll say I goes from 1 to n because we may have such n data points. So now we are defined the task of regression. You know that the task can be either of classification or regression. And as we saw that logistic regression, that actually is a classification algorithm. But here linear regression, it's actually a regression algorithm. So such that we see that this xi, it belongs to Rd. This means it will be a this data point will be a vector which will have d dimensions, and each value will be a real value. And the second thing is this yi. Now I told you that this is a regression task. So what's the meaning of regression? So these class labels will take a continuous range. So this will belong to R. This is how we define this. So as I said that mathematical equations, they are succinct way of representing a language. So if you right now see it, this is the data set. So now this is my data point. So one entry, if I write x1 comma y1, this is my one data point. So this x1, now it will have, this is a vector basically, it will be something like this, x11, x12, x13, and so on. Howsoever features it has x1d, because I said there are d features in this x1. And then this y1 is the label, as we are in this supervised learning setting. So in that, the labels and the data features are given. Okay, corresponding labels are also given. So now if these labels, if they belong to this R, if they take a real value, okay, then we call it a regression algorithm. If it takes some discrete values, let's suppose it yi takes values like 0, 1, 2 till k, some k class, we call it a classification task. So now you saw that the first thing that we saw about linear regression is it's a regression algorithm. That means the class labels basically will be a continuous range of values. And the second thing is it is a supervised machine learning algorithm. So in that we are given the class labels, and we are given the data point along with the class labels. It's not that we are just given the data points without any labeling. So here the labeling is done. Okay, so that's what I mean by regression. So what is a regression basically? It's a statistical method used to analyze the relationships now. So we'll see the relationships now. So let's suppose we'll have some variables like this. We can have a variable x and we can have variable y. So let's call this a independent variable. Independent variable. Or in mathematical term we call them variables. In machine learning terminology we call them features. Okay, let's suppose this over here is my dependent variable. So in machine learning what I'll call this as a feature, and I'll call this as my label. Okay, so if I have this x1, x2, x3 and so on till xd, so these are my features. These are my features. Let's suppose this is a data point x1, something like this, some data point x. Let's write this x1 like this. x2 is data point. So we can put a subscript also. Let's say I'll write it in some other format so that it's not confusing. So first data point, first feature. First data point, second feature. First data point, third feature, and so on. First data point, d feature. So this is my x1 data point. This. If I add x2, that will be x21. Second data point, first feature. Second data point, second feature. Second data point, third feature. Second data point, d feature. And all these are my independent variables. So they are my independent variables. So each of this is called a feature. So if I write it here, so each of them, so they are called as features. And this variable y, now it's a regression thing. So if you see y, it will take some real value. This y will take some real value. So this will be, let's say y1, then we'll have y2. So y1 can say, let's suppose in regression terms, it can be 0.5. This can be 0.08. This, or maybe y3 can be 58, something like this. Okay, this is a setting that we'll be working on. Now we have to see linear. So what's the meaning of linear? So in that we'll take some combination. So this is the features. If you now see them as variables, okay, we'll see them now as variables x1, x2. Now we'll have this variable x1, x2 till xd. Okay, and the subscript I won't write it because it's understood that it can be for any data. This is for general data point. It can be I should have written xi1, xi2, but now you should understood from this I am talking about a generic data point x. So now it is x1 over here, so we'll write 1 in front of every point. So now you have these many features, and now there is a corresponding label y, and this label now in this regression terms, it takes a real value. So what do I have to do is I'll somehow use a linear combination of these. Okay, so I'll multiply them with a constant factor. I'll find some factor. What I'll do is then I'll take a linear combination. So what I'm saying is I'm saying I'll write a linear equation. Let's suppose now I have this y and only x1. This is my only feature I'll have. So what I can do is, let's suppose I'll write something like this: ax1 plus b is equal to y. Okay, so this, you know, is actually an equation of line. Equation of a line. Why is it an equation of line? Because this a comma b, they are scalars, they are scalar values, so they are some constant values, and this I am not raising it any power. I am not giving any, let's suppose x1 square or something like that. I am just giving x1 linear term. Okay, that's the meaning of linear. So this is the simplest form of the regression algorithm. Okay, here what I said is y is a dependent variable, or it's a label, so x is independent variable. These features are independent. Okay, then what is this? This b is called as an intercept. This is an intercept, and this y is my label. Okay, and these are the coefficients. This a is the coefficient. I'm just showing you the mathematical treatment. So now there can be also the non-linear regression. So the regression is there. Now if you saw regression, so regression can be linear or non-linear now. So regression, you know what that is. If the label is continuous, now it can be linear and it can be non-linear. So what I mean by linear is I'll just use a combination of these things. If I had features like x1, x2, x3, so I have to associate my y with this. So what I'm saying is let's suppose y is equal some a1 x1 plus a2 x2 plus a3 x3 plus a4. Now if you see, there's a linear relationship between these features and the label. Why is it linear? Because I'm not raising this to any power. I'm not doing any non-linear function. And these are scalar values. a1, a2, a3 and a4, they're scalar values. So what is a non-linear regression then? Okay, if now these dependent and independent variables, if there is some non-linear relationship, so how I can show that? Let's suppose there can be a function involved now. So this y is equal, it can be a1 x1 square plus a2 x1 cube, something like this. Now you can see that here that this is quadratic, this is cubic term. Okay, now this is called as a polynomial regression. So if you talk about this, I'll call it a polynomial regression. Okay, this can be quadratic, cubic, howsoever. And then we'll have exponential regression also, where these functions are exponential, or maybe we'll have logarithmic function. So basically what I'm telling you is this y will be some function of x. Okay, now this function can be linear. Okay, then we'll call it linear regression. If it is non-linear, so in non-linear we can have polynomial, that is quadratic or cubic, quadratic, cubic, okay, or exponential, or maybe logarithmic. All of these functions are non-linear functions. And here if you see, if you see the linearity part where we have this line, okay, that's why it's called linear, because it looks like a line in 2D. Okay, so now if you see this, again summarizing, we had regression, that's basically where we have the labels that take a continuous range of values. Then it can be linear or non-linear. So linear means if it is of this form, so where we have this, the maximum power on these independent variables is 1. Okay, now you can have this polynomial regression also, where we can have cubic and quadratic, and we can have exponential, logarithmic, etc. Okay, is it clear so far?
Yes, sir.
Any questions?
No, sir.
So now if this is clear, now we'll see an example, and then we'll see what is our goal in the linear regression. So let's take an example, because things get clear when we take examples. As you know that somehow the size of a house has some relation with the cost of the house. Okay, So if you give me the size of the house, I can tell you the cost estimation. But you know that there is a linear dependence. Okay, what I mean by linear, let's suppose if I have this 1500 square feet, this is my 1500 square feet added SFT. So let's suppose it costs some 300k rupees or something like that, 300k dollars, howsoever you call it. And if I increase this to 600 square feet, okay, let's suppose now the increment is 320k. If I now increase again, if I increase 1700 square feet, so now you will see that this is 240k. So if I increase like by 100 square feet, you can see that the increment is somewhat around this. If you see 20k or 10k, okay. So from 300 it went to 320. So there is a gap of 20k. So here also there is a gap of 20k. And here if you see, I am increasing by 100 square feet. Okay, 100 square feet. This is what I mean by linear. By linear, I mean that if you see the change over here is 100 square feet. So okay, then the cost increased was 20k. Again, if I make the change, this 100 square feet, then again the cost changes 20. Okay, this is the perfect linear thing. Okay, where we follow the linear relation. Let's suppose if I ask you, if I have 100 square feet house now, okay, so what should be the cost now? Okay, and Amir, what should be the cost?
360.
360k. Okay, why? Because again I have to show the linear relationship. So if you somehow see these, and many of the real world problems, they follow into this category. So there, this label, so this is my label now, this is my label, and this is my one feature. Now you can see that they follow a linear relationship, but it cannot be strictly linear, it can be somewhat linear. Okay, and for that, because this linear regression is not a perfect algorithm, okay, this will be an approximation algorithm. Machine learning always is approximation. Rarely it is the case that we'll find exact results, and usually we'll find the approximations. Okay, and we are good with the approximations. So here if you see that these things, they follow the perfect linearity property. So now if you somehow capture this information, okay, you have to capture this. How can you capture this information? So what you can do is, you can say that, so how do I have this? I have some base price. Okay, I have some base price, then plus, okay, plus give me the square footage of house, give me the I'll say area of house, right? Let's suppose area. Okay, and then I'll multiply per unit area, something some factor I'll multiply here. I'll give you the cost of house. Okay, so what is given to you? This area is given to you. So this is given to you. Okay, now you will have to find this quantity, and you will have to find this base price. So if you see over here, so you saw this 1500 square feet, it was related to 300k, and then we went at 1600, so this was 320k, and then we had 1700, so this was say 340k. So that is the result that we have. Now we have to somehow fit into this realm. So we should have some base price, then plus howsoever your area is, then multiply with that, and now we can get it from this relation. Okay, so we can get that from here. So let's suppose the area was 1500, so area was 1500. What should we multiply here? So now if you see that, I can make equations. I can make two equations. So how can I make equations? So I can say, let's suppose base price is B, plus my area is, let's suppose capital A, and then this is say M. M is the per unit cost. This is equal to, let's suppose, some Y. Okay, so the first equation tells me that, if you see the first equation, let's suppose base I don't know, plus area I know 1500. Okay, M I don't know, but you know Y. So for this there is 300k. And then for the second example, if you see, for the second example, you have this 1600. M I don't know, B I again don't know, and this is equal to 320k. Now you see that these two are unknowns. This M and this B is unknown, and everything is known, rest is known. Can you solve this equation? Anyone? Can you solve these equations? So these are just linear equations.
Yes, sir.
They are linear equations. Now you can solve and find the values for B and M. You can find the values for B and M exactly. Then once you have the values of B and M, let's suppose the values for B and M, you got some value. B is equal to 20, let's say 20. I'm not solving the equation. B is equal to 20 and M is equal to say 30. Now if somebody says you area is 1800, so what you can do is, you can say that I know there is base price plus this M, this area, and then this is my area, and multiplied by this M. So this will give me the cost. Okay, so what is this b? So this b is 20, area is given to you 1800 and multiplied by m also you found from the data, so that's 30 and you will get the cost. This is how you find the cost. So basically what are you doing is you are just solving the linear equations. Is it clear? Is it
Yes,
clear?
sir.
So now what you try to do is basically, if I show you geometrically, let's say a geometric interpretation, if I show you geometrically what happens. So in this 2D, let's suppose we have this 2D plane. This is our 2D plane, and we are here we had a feature, let's call that feature x1. Okay, here we want the cost. This is our square footage. Let's suppose this is square or area of the house. Oh, sorry. I hope this is visible. Huh? So here this is the area of the house, and here this is the cost. Okay, and now what I'm saying is if I give you some data point over here, so data you will see lies something like this. So if it's perfect linear, then what you will see is basically when you are finding the values for these, whatever I called b and that m, okay, and you are basically finding this line y is equal to mx plus c or mx plus b, I'll write now. Okay, so y is equal to mx plus b. This y was my cost, okay, and this m, this was my whatever per square feet cost. Okay, this x was my area, and this was my base price. This was my base price, so I'll write it here. This was my base price. Okay, and now you found a line. Once you found this m and b, now you know that you can uniquely draw a line. So that line will look something like this. It would not be permanent. Let's suppose this is the line that is there. Okay, and you try to what you try to from these were my data points. Okay, so what was this data point? Let's suppose this was the first point that we had 1500 square feet, and the cost, if you saw, let's suppose this cost was around 300k, and this was my second data point, which was 1600, and let's suppose the cost over here was 320k. Okay, similarly this was my 1700 point and the cost was 340k. This is how I'll show it geometrically. Okay, let me also show you the graph that I have plotted for you people in matplotlib so that you get the clarity. Give me a sec. So you can see this graph. So over here this is my price, and over here this is size in square feet. Okay, so now what is this line? If you see over here, this is basically y is equal to mx plus c or mx plus b, I wrote. Okay, so this y is my cost, this x is my area, and this m is the cost per square feet, and this b is some base price. Okay, the initial price. Let's suppose if you have the smallest house, let's suppose smallest house may not start from 0, so it may start from something, and you still want to give some base price to that. Okay, and this is the line that I drew in the previous picture. I hope this is clear. Is it clear so far? So if you now see, so in the 2D problem, in the 2D realm, you are just having some features. Okay, if you just had two data points, you could exactly say, okay, what is the line passing through that. So now in the real world sense, the problem won't be much simple. The problem won't be like this. So the problem will be something like this. You'll have a point. They won't follow the linear relationship, but it will be almost linear. Okay, it won't be linear, but it will be almost linear. So if you see these points over here, so here we can figure out that they are somewhat linear, but they are not exactly linear. Okay, let's make it a bit clean. So if you see right over here, so this is my feature. Let's suppose this is my feature x1, and this is my label y. Okay, and this is the regression problem. Okay, because this is my point. If you just tell me the feature, that's a feature value, and this is the corresponding label value. Again, feature value, this is the label value. Okay, this is y is continuous values. So if you see this data is not linear though. Okay, so but it is somewhat near to linear. It's nearly linear. Okay, it's not perfect linear. Why? Because you cannot find equation, you cannot find the values for this m and b which satisfies all of these. Otherwise, that whatever line you find, whatever m and b you found, that should be passing through all the points. But you can clearly see that that's not possible over here. Okay, so if I just draw a line, let's suppose something like this, and if I try to best draw a line so that it touches maximum points, somewhat like this, let's suppose. Okay, but still you can see that this line is not perfectly fit over there. Okay, because this data is linear, it looks somewhat linear, but there is non-linearity also. This data is actually non-linear, but it is nearly linear, because if I just fit a line onto that, I can somehow approximate the values. Okay, if I get for this data point, I'll get this error, for the data point I'll get this error, I'll get this error, I'll get this error. So this is what the linear regression does. So it tries to fit a line, so it tries to fit a linear surface, rather it tries to fit a linear surface, linear surface, okay, onto the data. Let's suppose if I fit this line, so what this line should be, that line should have very less error. Okay, okay, the thing is that error should be very less, error should be least. Now you can ask me that there are infinite lines possible. I can also draw, let's suppose, this line. Okay, I can also draw this line, which somewhat is again linear. But if you see this, this red line basically is the line which will have least error. So what I mean by error, I'll have to define this error. So error is how much is it deviating from the actual value. So we'll predict something, we'll predict, so let's suppose y hat we'll call it, this is my prediction. Okay, and this y is my actual thing. Okay, what I want is the error, therefore the error is, if I see you the error is y minus y hat is the error, this is the error, and somehow I want to minimize this error, I have to minimize this error, minimize the error. Is it clear for everybody? Is it clear?
Yes, sir.
Okay,
Yes, sir.
the point I'm saying is you should give me one thing. So what I'm saying is you have the data which is actually not linear, but it is linearly linear. So there is the things here and there. So if you see in our linear algebra terms, there will be no solution to the equation. So there will be no line basically which passes through the every point. Okay, if you write all of these equations, then there will be no simultaneous values which satisfy all the equations. So as you saw it here, so you can, this was perfectly linear in our example of this house price prediction. So it was perfectly linear, so we could find b and m so that it satisfies all these values. But if you now found m and b, so now you know that these points, they are not perfectly linear. So these points over here, they are not perfectly linear. So now what I want is, I know that it does not lie in the column space. Okay, coming in the linear algebra terminology, you should watch that lecture again, so as to now you'll get the perfect picture. So actually there is no solution that exists. So but what I'm saying is, now I'm saying, can I make a solution such that the error is the error is minimal? Okay, I'm okay with the approximation, but can I do something so that whatever line I found, that line should give me the minimal error? Okay, so the error, what is the error? So error, I defined it like this. So whatever, this was the actual prediction. Okay, but I predicted it like this, so this is the error, this red part is the error. So this was my actual, but I predicted it like this, so this is the error, this red part is the error. So for all the data points, I want this error to be minimized. Okay, so this is how I define error, this is one way to define error. So we can define errors in multiple ways. Okay, let's take an example in 3D. Now we just did this linear regression for 2D. We have, let's suppose, size of the building, and then the cost associated with it. Let's suppose now we'll see size and the number of bedrooms. Let's say now the data is like this. So data 1, so feature 1, let's call that x1 feature and x2 feature, and then we have label y, this is the cost. Say this x1 again, this x1 can be still the same thing, let's call this area. Okay, and let's call this number of bedrooms. Okay, and this is now size. So somehow what I can say is, again if you see, this y is somewhat related to these two. Now I'll have to assign the weights. Okay, so assign some weights, let's call that weight w1 and w2. I'll assign some weights to all these, and okay, the importance basically, I can write it w1 x1 plus w2 x2 plus some w3 or w0, let's call it, is equal to y. Okay, so I'm just assigning some weight to here, I'm assigning some weight onto this, and I'm computing this y, because I know somewhere this is the linear relation. Okay, let's again draw it, so this is my one axis, second, third axis. Let's say this is my x1 feature and this is my x2 feature. Let's say this is cost, this is y. Okay, so this is my number of bedrooms, say, and this is my area. So let's suppose this is the point, so this is my data point. Okay, now if I want to predict, okay, what I'll do is, let's suppose the prediction comes out to be this. Okay, so this is the corresponding area. Okay, and let's suppose now for, if I write it like this, I'll get some points like this. Okay, some points. So now what I'll try to fit a plane onto this. So plane will somehow look like this. So all these points should lie on the plane. But if this data is not perfectly linear, so what, there will be some error. So let's suppose prediction should have been this, but it predicted it somewhere around this. This is the error. Okay, let's suppose this is not perfectly on this plane. So but if it is perfect on the plane, the error will be 0. So most, for the most of the points, the error won't be 0. But what I want try to do is, I want to fit this plane. So this is till what we can imagine. We can imagine till only through 3D. Let's show this in Matplotlib. Okay, I'll show that so that it becomes clear, because my drawing is pretty bad. So I'll show this in 3D, this in the VS Code. So if you now see over here, so now this is my square feet. This is, let's suppose, my x-axis. This is my y-axis, and this is my z-axis. That is the price that's predicted. And if you see, these are the points. This is my one point, and this is my other point. This is my other point, and this is the plane that fits it. Okay, because now you know the equation of the plane. How to write the equation of the plane? The equation of plane is w1 x1 plus w2 x2 plus w0 is equal to 0. This is the plane. Equation of the plane. Okay, and this is the equation of the plane in, let's suppose, 3D. This is 2D plane, basically 2D plane. Or I can just write plane, because plane is 2D. Okay, if I have now line, so line is w1 x plus w0 is equal to 0. This is my line. Where I say y is equal to mx plus c. Okay, so y is equal to mx plus c. This is the equation of the line. Okay, so here if you see, you just put in these values. This 0 basically means I am letting it passing through the origin. This is what I am saying. The line is like this, something like this. Not even, if I put w0 is equal to 0, so that I am saying y is equal to, if I say wx y1 x1 plus 0, this is the line passing through the origin, something like this. So but we had a detailed discussion on the initial lecture of linear algebra on this, so I hope that this is clear now. By now this should be clear. So this represents a plane, this represents a line. So if I just write, let's suppose, something like this: w1 x1 plus w2 x2 w2 x2 plus and so on till wn xn. So suppose we are now in n dimension or d dimension, let's suppose, because our point line d dimension xd. Okay, plus w0. Okay, so this will be a hyperplane. So this is an equation of hyperplane. This is my hyperplane. So we cannot imagine it, we can only imagine. Let's suppose I'll just cover this VS Code over here. So this, if you see, this is my equation of plane, this is my equation of line, and this is my equation of hyperplane. So if you see this x1 x2 till xt, so they can be thought as features, and these w1 w2 w2, they can be thought as weights. Okay, how much weight do you assign to these things? Now the thing that we are doing in linear regression is, we are trying to find two parameters. We are trying to find this w's, and we are trying to find this w0. Okay, by w's I mean I am trying to find w1 till wd, and this w0 basically is my intercept term. Okay, intercept term, and this is my weight vector. Weight vector, and these two things basically define a plane. Okay, they define a hyperplane. I'll call them hyperplane. Is it clear so far? Any questions?
No, sir.
Okay, so what I'm saying is, you see that we have to just find this w's, and we have to find this w0. These are the only two things that you have to find, but subject to, there is a condition. Now the condition is that error should be minimum. Error should be minimum. That's the thing that you have to, error should be minimum. Now we have to define the error. So in the error, what I said is, I said error is basically this. It will take this y hat, whatever is prediction, this is my prediction, and this is my actual thing. So I'll write it, this is my actual label, and this is my predicted label. Predicted label. I'll somehow have to find the error. So what I said is, I'll subtract these and I'll find the error. Okay, now I'll have to minimize this error. Okay, I'll have to minimize this. So I'll write, let's suppose, this y I hat minus y should be minimized. Okay, now there can be positive errors. Okay, there can be positive errors, and there can be negative errors. So what I mean by negative error is, let's suppose positive error means this yi hat was greater than y. Negative errors mean yi was less than this y. This yi hat was less than yi. So now I somehow want to generalize it. So if you see this, so there will be positive and negative. When I sum of these errors, okay, so some positives will cancel the negatives. Okay, now, but I just want to error. So one thing is, I can put the absolute values over here. I can just put it like this. I can put the absolute value, so that this will give me the absolute error. So this thing over here will give me the absolute error. Let me write that separately so that I don't. This is the normal error. So you saw the problem with this error, because some errors will be positive, some errors will be negative. When I sum them up, sometimes the errors can be zero, because what are the positive error I had, it can be I had the same negative error, and they'll cancel each other out. But I don't want that. So what I want is I want absolute error now. Okay. So what is why is that happening? Because let's suppose this is my line that I drew, and this is the point, one point. This is other point. Let's suppose this is one point and this is other point. For this, this is the error. Let's suppose this is positive error, and for over here this is negative error. Now if I combine these two things, now they'll cancel out the error, and I'll feel that I have no error. So for that purpose, I need some absolute error. Okay, I need absolute error. I am not caring about the positive error and negative error now, because there is a problem with that. It'll in the summation term, it'll just cancel it out. So what I'm saying is, I'm worried about this absolute error. So what I'll do is, so the thing that I can do is, that is y I had minus y, I'll put absolute value. Okay, now this is like absolute error. So now the problem with this is, how do we like minimize the things? We usually minimize the things by using differentiation. Okay, by using the tools of calculus. So there we would like to we like a function to be continuous and differentiable. So the second thing that we can do is, we'll do one thing. We can define error something like this: y I hat minus y I whole square. We'll square the errors. Okay, and we'll try to minimize this error. That's why this is called as least squared error. Squared error. Okay, what was this? This was absolute error. Absolute error. So what is this error? So this is my squared error. Now I want to get least squared error. I want to get the as least as possible. Okay, absolute error is when you have this. But this is a normal error. This is just error. So it has positive terms and negative terms as well. So now if you see over here, so we can have absolute error. But I told you that once you try to minimize the error, so we use tools of calculus where the function should be differentiable. And if you know this modulus function, it has problem. It has something like this, some graph like this. Okay, some V-shaped graph. Okay, it gives hard time while you differentiate and you check its continuous. But if you see this x square graph, that's quite smooth graph. The graph is like this. Okay, that's quite smooth and it's easily differentiable. That's why it's called square error. Now our job is, we want our error to be minimized. Our error should be minimized. So how to minimize the error? Let's write this expression now. So we want to minimize this error. So our goal is to minimize squared error. So that's called, we want least squared errors. Least squared error. Okay, so for all the points, I'm summing up error for all the points. So y I hat minus yi whole square, I goes from 1 to n. These are my endpoints. For all the points, I want to minimize this. Okay, I want to minimize the equation now. So if you see how I can write it, I can also write it like this: minimize summation of I is equal to 1 to n. So this is yi, you know how it was predicted. So this was predicted by w transpose x. This is my ith data point, I plus w naught minus yi whole square. Okay, this is how it was predicted, and this I can write it like this also. So basically, we want to minimize this expression. Is it clear? Is it clear?
Yes, sir.
Okay,
Yes, sir.
this w transfer, basically this is something like this: w1, w2 till wd. This is a row vector, I call it, and then we have this w naught. So xi means, so we have this xi1, xi2 till xid. Okay, and this is the plus w naught. Okay, and then now you know this yi also, because this is our yi. So over here, this yi, I just expand it over here, because that's how I am basically getting this value of yi. I'm just writing it in expanded form. Is it clear so far? This should be crystal clear. This is the
Yes,
thing.
sir.
This is the thing that we want to do. This is the thing that and now, what is the parameter that we want to find? Okay, so now we will write that you have to somehow minimize this error. Okay, now you wrote the minimize. We'll write something like this. We'll say argmin, minimize this. Argmin on w, because we can only find this w and w naught. Argmin on this w and w naught. Okay, we'll find this w and w naught such that this thing is minimized. Okay, that's the meaning of argmin. So I'll write argmin of this summation of I goes from 1 to n, and w transpose xi plus w naught, w transpose xi plus w naught minus yi whole square. Okay, so basically you have to find such w. Okay, you have to basically find this w naught, w1 not W naught, so W1, W2 till WD, and this W naught, such that this error is minimized. So this is what you have to find. This is the thing that you have to answer. So what are the parameters? So we'll call them parameters. Parameters of linear regression. So what are the parameters in linear regression? So the parameters in the linear regression are this W1, W2 till WD. So this is what we call as a weight vector. So these are the parameters. This weight vector is the parameter. And the second is this W naught. We call this an intercept. These are the parameters. Is it clear so far? Is it clear?
Yes, sir.
So if you understood all of this, so now what we'll do is where to apply this linear regression. Okay. So when you are seeing some data, what you should see first. So where to apply? Where to apply linear regression? Because for every algorithm we did this. We said that every algorithm basically works on certain assumptions. So there are certain assumptions about the data. Assumptions about the data. Okay. Under these assumptions, this algorithm works better. So if the assumptions are not followed, so more or less you will see that the algorithm start giving the more, and it does not fit the best. Okay. So what I said is the first thing is linearity. Okay, what is meaning of the linearity? I actually explained that. I said that relationship between these features and the label should be somewhat linear. It may not be perfectly linear, but it should be linear. Okay, so how we can do that? You can visually see the data. Let's suppose you can plot the data. If you see something like this, okay, you can say, oh, there is some visual relationship. You can do that by plotting. Okay, if it's multiple regression, also you can plot that in 3D or something like that. And the second thing is that there should be independence. Okay, independence. What is the meaning of independence? So let's suppose once you are computing this, you have multiple points, you have multiple observations, we call them in machine learning. So once you have these observations, okay, the dependent, these let's suppose we have this y, that is the dependent variable. This, its value should not be influenced by other point. Let's suppose you have point x1 and x2, okay, and correspondingly you have this label y1 and y2. This point should not have any impact on this point. So whatever the label we had over here, let's say we had y2, this should be not impacted by the label y1. They should never be impacted previously. What are data points we have? So why is this violation usually? Usually in time series we have such things. So in time series data we have such things because previous label has an impact on this. Let's suppose stock market. So where the stock market closed today, it has somewhat impact on tomorrow's stock market. Okay, there is some what we can call dependence. So in here the assumption is that data is independent. The first thing is linearity. So between these dependent and independent variables, basically features in the labels, so there should be this linear relationship. And the second thing is independence. Okay, so these are the two things which are very important. And there are other things also, like the error should basically come from the error, that whatever the error residual error, it should be coming from the normal distribution. But we'll see that what that means. It should come from standard normal distribution, usually they call it. This is standard normal variate. We have also seen that. But these are the two important assumptions about the data. The first assumption is that between the features and the label, so there should be a linear relationship. And the second is that the data points should be independent. They should not have any dependency as in time series. Okay, I hope this is also clear. So now the thing is, we also somehow saw the error. So okay, so what we saw is we have to fit I'll call a linear surface, fit a linear surface on data. Surface on data. And the second point is which fit linear surface which has least error. Least error. Okay. Now we quantified the error. So the thing that we quantified the error with. Okay. Now we'll give some values to these. So we'll give the values W's and this W naught. I'll just write that big W and this small W naught. So these are the two values. And we must pass it via a function. Okay, and then we'll see how much error there is. So this is called a cost function. So this over here is cost function. Okay, or loss function. So I have I think multiple times told you what a cost function is and what a loss function. So here what you see is, if you give there are two types of function involved now. Don't get confused. So the first function that we saw is, let's suppose, this linear function that we had. The actual curve function, I'll call it a linear function. Okay, curve fitting function. So you are having that's less of plane. That function was W transpose X plus W naught, okay, is equal to 0. So this was the function, the plane. Okay, and you will now give multiple values. So there can be infinite planes possible, infinite planes possible. This is really important to understand. So what I'm saying is, so there are two functions now. The first function is this, the function of plane. So for which you want to find this W transpose and W naught, so that you just fit in the values and you get a line or a plane. You will get a line if it is this W1 x1 plus W naught is equal to 0. You will just find the values of W1 and W naught. You will find a line. Let's suppose that line looks something like this. Okay. You just want to find that perfect W1 and W naught. So the second function I said is called as cost function. So what is that cost function? That cost function will basically take the values, this W, big W, and the small w. So it will give you an error. This again is a function. So this over here is again a function. This is called as cost function. So now what will this function help you in? So this function will help you in deciding which is better. So which line is better. Let's suppose for the values W1 and W naught, let's suppose we have values 2 and 3, we have values 4 and 5. So this will be one line. Say let's suppose like this. This line will be like this. Suppose 8 and 9. So this line will be something like this. So among these, because when you change the values of this W and W2, this is just in the linear surface I'm talking about, on these 2D surfaces. So once you change the values of this W and W naught, you are getting different lines. So this cost function is basically telling you how much error is there. So the actual data, basically you will see which line fits the actual data best, and you will get the error from that. Is the distinction between two of these functions clear? The first function that we have is basically curve fitting function, or we call it the linear function, so plane function, the function of the plane. The second function is once you decide on these, okay. So what is this cost function? This we have two functions. One is cost function. So cost function basically takes these w's, this W naught and big W as an input, and gives an error. Okay. If you found that error to be minimum, let's suppose you will check it with multiple costs. You'll check it with multiple W's and W naught. Okay, and then you will see which of these W's give the minimum error. So once you have that, so now this is your input data. Okay, from the input data you will check this. Okay, and now this is your actual what I call as curve fitting function. This is not just curve, because a line is also a curve fitting function. So there you will give this W and W naught, whatever give you the least error. So this will basically give you a plane, something like a line, or maybe a plane, or I have a plane, something like this. And this will be the best fit. Okay, this is called as the best fit. So what is the best fit? Where the error is minimum. What is the worst fit? Where the error is more. Okay. How many for how many of you people is this clear? Is this this curve fitting function, or we call it plane function, and this cost function clear? Okay, this is really important to understand, because sometimes we mix up these two things. We say cost function is some function, this is related. So cost function basically gives us this quantifies our correctness or wrong, our correctness. So how much correct are we? Okay, or how much wrong are we? So okay, this is the quantification of that. Cost function is basically the quantification of that thing. So if you want to quantify that thing, if I have this W and this W naught, if I pass it on to cost function, so how is this cost function evaluated? So this will be evaluated by all the points. So it also takes all data points. So it will check with all data points, and this it will give you an error. Okay, this basically takes this W and parameters. So cost function is there. So cost function takes the parameters. Okay, and it takes the data points as, let's suppose, as an input, and then it computes the error. This error tells you how much better these parameters are, and then based on this cost function we'll adjust the parameters. Now the question is that, as we saw, that we want to minimize, coming back where we left. So this basically is a cost function. If you see over here, okay, we want to minimize this, we want to minimize the cost, or we want to minimize the error. That's why it's called loss function, cost function. Okay, so now we want to minimize this. Let me select this over here. Okay, let me select the function and take it on the other page. So if you, this is my cost function now. I'll paste it over here. Now I want to somehow minimize this. I want to find the argmin. What is the meaning of argmin? Find such W and W naught. Okay, such that this equation gets the minimum value. Okay, I'll have to minimize this. So what are the tools that I have? The first thing I'll say is the tools that I'll have. Okay, the one tool is called as OLS. Okay, ordinary least squares. So in that we'll use calculus. Okay, and the second thing is sometimes this method becomes computationally heavy. This becomes computationally heavy. Okay, then what we use is that's called as gradient descent. These are the two methods by which we can basically find an optimal value. So we want to optimize this. We want to find optimized value of this. So for that, the first method that is there is called as OLS. Okay, and the second method is called gradient descent. So this gives you the closed form solution. Closed form solution. So what I mean by closed form, this directly gives you value. Okay, this is your b. What should be the value? It will give you an equation. You just come on to compute that equation. And the second thing is, it will give again the equation for w also. So it will give an equation for w. Let's suppose you want to compute w1, an equation is there. For w2, an equation it will give. Okay, once you solve it by this. But what gradient descent does is, gradient descent is somewhat, I'll say, an algorithm which adjusts the value accordingly. We'll see what gradient descent is. Okay, and there are different versions of gradient descent, and this gradient descent is heavily used in your neural networks. Okay, so from there, so the first thing is, this also has closed form solution. Also, the closed form solution we can get this by OLS. But let's suppose you have to find, say, w1 till w100 with this w naught also. So you have to find how many 101 parameters. So now if you want to compute the closed form equation of all these, so closed form, you will have these many number of closed form equations. So each of them will have like their own this computational complexities. Let's suppose the equation is something like this: w1 is equal, let's suppose, some xi data point minus x bar into I minus y bar divided by summation of something like this. Okay, so for all data points, you will go through all data points and then find w1. You will go again through all data points, find w2. Okay, if you have only 100, you will go 100 times to the whole data in order to compute this. This is just a single example, and sometimes the parameters can be at least, let's suppose, if your features are, say, 500 features, so it becomes computationally heavy. So it's better, what we do is, we then at that time use this gradient descent algorithm. So gradient descent algorithm is one of the techniques by which you get the optimal solution. Okay, this also has roots in its roots are also in calculus, but these two work differently, because this gives you the closed form equation and this gives you the parameters and tries to adjust the parameters. It will give, let's suppose, first it will give you some parameters, say w and w naught. So you will find, okay, you will find the error, let's suppose, is someone e1, and then second time what it will do is it will adjust the parameters. So it will adjust the parameters such that we have this, what is happening, and we have this w dash and w naught dash, and this e2 is there. Okay, and it will sometimes make sure that this e2 is less than or equal to e1, so that we are minimizing the error. And once it sees that, and sometimes it takes multiple epochs to by epoch I mean multiple steps, I can say. So this is some stepwise procedure, stepwise. Okay, and it's an iterative based algorithm. So what I'm talking about, gradient descent. So we'll see what gradient descent is, but here you should be clear that this OLS is a closed, it gives closed form solution to each of these parameters, and this gradient descent is an iterative based approach. So what it does is, it will first estimate something, okay, then improve its estimation, again see something, again improve, and it will keep on improving and keep on improving till we at least find what's called as convergence. So we don't see much change, and then we'll see this is the optimal thing. And sometimes this can give you suboptimal answers. It can like get stuck in the local minima also. But this OLS algorithm for the linear regression, what it gives you closed form solution, closed form. Okay, for each of these w's, it will give an equation, and you will have to solve that equation by using the data points, and then you will find the values for these w naught, w1, w2 till wd, and you will get the answer. Okay, and we'll take this OLS and this gradient descent algorithm in next session. Once we are done with that, we'll do probably a small project, so that you get to work on something, and then you'll receive an assignment based on that. And after that, till you cover your probability part, we'll again come back to logistic regression and its probabilistic interpretation. And this also has a beautiful probabilistic interpretation. This linear regression also has beautiful probabilistic interpretation. We'll also see that. So these two things probabilistically, we'll see that after you went through the probability assignment. And but in next session we'll cover this OLS and this gradient descent, and we'll probably solve a small project onto this. I'll stop recording over here. If you have any questions, I am willing to take that.